Lauren, can you hear me?
Tu es trop grand pour comprendre des choses aussi petites.
Dr. Laurent, good afternoon. Can you hear me?
Hello?
Yes, your audio is okay.
Vous allez étudier à l'instant.
Hello? I cannot hear you. Okay. Hello. Hi, David.
Professor Javed, can you hear me?
Oh, yeah, I can hear you.
Okay. There is a Dr. Devapriya Datta may come bit late, maybe 5-10 minutes late.
Okay, fine. Okay.
This session should start at 4:30.
4:30. It is 14 minutes.
Okay.
And the session is for 1 hour.
Professor Purti. Yes. Please unmute your Professor Purti.
Sir, ನಿಮ್ದು ಇದು ಮೈಕ್ ಆನ್ ಮಾಡಿ.
Yes, Putty is here.
Yes. Good afternoon. Good afternoon. And all things are okay. Let us see. So, and
Professor Datta, there is a small question.
Yes.
We have 4 experts on the panel today.
Okay.
A small introduction has to be given from your side. Will someone be doing that?
No. Introductions to this board. You are sending.
I have sent for the first 2 and the next 2 are there.
These things are with you. First, Professor Javed,
Okay.
you have that. Just you introduce because that will be continuity will be there. You just take the mail. Access has just sent the mail. Dr. Javed, just wait for some times.
Yes, yes.
Just wait for some times to. Professor Nandagiri has joined. Can you hear me?
Professor Datta. Professor Datta.
Good afternoon. I can hear you.
Yeah. I had a question for you.
Okay.
Do you have any database of researchers in hydrology, both Indian and abroad?
No, database we don't have. No, I don't have.
You don't have a list of people?
No.
Email IDs?
No, just a few I have that who are my contact, like some are northeast.
No, I think we should all sit together and make an effort and create this kind of a database, you know?
Yes, we can create it and we can have it. So that will be good.
So that for all such events,
yes,
it can be a mailing list which all of us can share.
Yes, we can do it. We can do it. These things I can, from IIT Guwahati, I can take initiative. That's not a big issue.
Oh, okay. So if you can ask one or two of your students to sit and visit all the websites and get it.
Yes, we can do it. That's we can.
Sir, Professor Nandagiri,
yes.
I think this should be part of the open floor, okay?
No, this was off the record with Professor Datta.
No, make it official and bring it onto the open floor.
I'll raise that also. I'll bring that up.
Yes, thank you.
I think we can suggest Professor Nandagiri and Professor Poti that we can also start some offland hydrology society. There are the society, but we can talk about.
Yeah, sure. Yes, so absolutely.
That way, if we have a society, okay, slowly all the activities will start in.
Correct.
So we can start in this Himalayan, Western Himalayan, or upland areas. We can talk about it.
Are you a member of IHS?
IHS, I am.
You're a member.
Yes.
But we rarely get to know what is happening in IHS. Who is the Indian representative?
Yes, that's true. That's true.
Because that is a very important link to the international community.
Yeah. Yes. Like for example, this this Indian Society of Hydraulics, there's a good group, okay. But in hydrology, it comes like a sub-component there.
Correct.
So because they have oceanography and all, so I think this is the time has come. I think we can talk sometime. I think I'll discuss with Professor Poti and you. We will think appropriate titles and let us have one society on this.
Sure.
Start in the city, I can start it. So that's not a big super nice.
Good idea.
Hello, Lakshman.
Hi, Laurent. How are you?
I'm fine. You remember in 2015 we had a workshop organized by Vina, which was aimed to. It was in some resort, but it was close to the airport somewhere, I think, and it was aimed at bringing together a community of hydrologists. So maybe you can start with that. No, there is a long list there.
Correct. So, how are you, Laurent? How are things with you? All fine? Did you get a chance to go home?
No. I cannot travel now, no. And France is in lockdown, so.
Okay.
Oh. How long it is lockdown?
It started beginning of November, and it was announced for 1 month, but everyone believes that it will be extended.
So there's a second wave which is happening.
Yeah, there is a big second wave, yeah. And they did that probably because they wanted to reopen for Christmas festivals and this at the end of the year, but let's see what happens.
Sad, yeah. So Javed, who else has to join?
So we need Mr. Kirit Kumar should join. And then Dr. Debapriya Datta should join. We have 4 experts on the panel, and then I see only 2 experts now. So we require the other 2.
Professor Javed, actually we are contacting Dr. Kirit Kumar, so he is going to join it. There is some problem.
Fine, sir. Okay. Now, Debapriya Datta, Dr. Debapriya Datta, I heard would be joining a little late, 10 minutes late.
Little later, 10 minutes later, what you say.
I assume that Shri Kirit Kumar would be there on time, sir. Is it?
Yeah, within 2 or 3 minutes.
Oh, yeah, sure. The moment Shri Kirit joins us, we'll start the session.
But Javed, do we have an audience? How many people are there?
That I would not have an idea, sir. I think that should come from Professor Datta.
As of now, audience 16s are there. 16 from this MS Team Live, YouTube Live.
But on the YouTube?
YouTube, just wait a second.
Because most people would prefer the YouTube.
Yeah, yes, that is quite easy.
Quite easy. Especially on the mobile phone, YouTube is much easier.
It's about 27. 27 excluding this panel. So that's okay, not bad.
I think there's one more thing to this workshop. We would be uploading these proceedings, the addresses and presentations, and then that would be there for a long time. And I think that would have a bigger audience than what we are having live now.
Okay. That's good. That's good.
Hey, Javed, shall we? Hey, you should start. I think it's not getting late.
I think,
Maybe attend. Okay. I think, sir, you have joined as a attendee there, sir. So you so can you please I mean, if you have.
hello, Professor Javed. There is a slight bit issue for connecting this MS Team live. So wait for 1 or 2 minutes.
Yeah, sure, sir. I mean, that's not an issue. The only issue is the other participants would be online.
Yeah,
for this to start.
That's good. That's good.
Okay. Yes, sir. Yes, sir. Okay, but can you please check, sir, whether this on top of your this Google, are you using Microsoft Teams app or is you are using Kuwait, sir? Okay, app. So on top, sir, can you please check is it your account or is it the Microsoft the account we have provided? Can you please check once, sir? On the right hand. Yes, sir, please. Right hand top corner. Sir, right hand top corner, there will be a circle there on this cross button, this minimize button is there, no? So just your name, I think should be there. That. Instead, what is coming, sir? Can you please tell me? Field Hydrology Research, yes, it should come like that. Yes, sir, that is okay, sir. Can you please just click the link that we have shared with you? No. Then if it is showing like that, then there will be an option below that you can use you launch your app. So you just click the link and we will guide you. Please click the link.
Professor Javed,
Yes, sir.
I think you start the event. Let the other two present it. There is some issues on network connectivity.
Fine, sir. Yeah.
So you just start it. We are sorting out that part.
Okay. I think if they cannot join, maybe they can be replaced by our people. Okay. Maybe Dr. Datta, you can join, and then maybe Dr. Putti can be the panelist now. If by chance, if they don't join. Sir, Datta, your mic is off. Your mic is off.
Yes. So we are starting now. We are starting now. Putting you to the live.
I have put on the mic. I am ready, but may not be in a position to discuss things. Yes, come on.
Okay. I'll do it. So, Professor Javed, you can start it. We'll put it in the live.
Yeah.
Yes.
Thank you, Dr. Datta. Can you please put the PPT that I had sent? Ashish knows the PPT. Yeah, thank you. I'm Dr. Javed. I work as a professor in National Institute of Engineering, Mysore, quite an old college, and we have a master's program, and then we have some experimental watersheds in the Western Ghats, where we do the field work with our master's degree students, and then also the PhD research scholars. Now, I have been working here for almost about 30 years. I'm happy to chair this session, and this is an open floor. And I thank the experts that are present on this panel. I'll just very briefly introduce who are on the panel today for the discussion. We have Professor Nandagiri. He's a professor from NITK Surathkal, and his experience is about 35 years. And I apologize for not giving a detailed account of our biodata and resume about these people, the experts present with us, because we are very short of time. So I'll go ahead with very brief, introduction to these experts that we have with us today. Then and it's very obvious that they have a big lot of research publications to their credits, and almost about 35 years of research experience connected with them. We also have Dr. Laura Roes. Is a research engineer. We have an organization known as INRA. It's a government organization in France. He's a research engineer there. INRA stands for National Research Institute for Agriculture, Food and Environment. And very special about Lara and why we wanted him to be part of the panel today is he has also been working in India in the field of hydrology since 2000, almost for about 20 years. So he has an experience both in India and also in France as far as field hydrology is concerned. Then we have with us Shri Kirit Kumar. He is a mission director, and then he is the mission director for National Mission on Hydrological Studies. I think it is. I'm sorry. I think it should be Himalayan Studies. Okay, National Mission on Himalayan Studies. He's the mission director for that, and his basic interests are in environmental engineering, hydrology, and water resource management. And after this, we have the fourth expert, and that's Dr. Debapriya Datta. He is the head NRDMS. As you all know, NRDMS stands for National Resource Data Management System, and it comes under DST, and he works from Delhi. And he has Dr. Debapriya Datta has a PhD from Indian Agriculture Research Institute, New Delhi, and his expertise and research interests are in application of geoinformatics for natural resources management, watershed management technologies, geoinformation management, capacity building for local level planning, international science and technology cooperation in the context of sustainable development goals. So this is a very, very brief background. I apologize for not giving an exhaustive background of these experts, but be assured that all of these people, these experts have experience not less than 35 years in their varied, what do you call, research areas. Now, the theme of today's open floor is a road ahead for field hydrology issues and concerns. I would like to brief you about this theme a little. Even though the country is advancing fast and fairly well in other realms of sciences, particularly in the field of data sciences, the health of hydrology does not seem to be that well in the country. Professor McDonnell, in his article titled Wither Field Hydrology, published in Water Resources Research, talks about the decline in fieldwork worldwide. This may also be true in India, but we have also deeper problems and issues ailing hydrology. It has to be noted that the practice of hydrology in the premier institutions in the country is not a complete indicator of the health of hydrology in the country. There are thousands of tertiary level research and teaching institutes in the country. One of the most important indicators comes from these institutions. How well is it being nurtured and practiced in these tertiary institutes would be a very good indicator. I meant how well is hydrology being nurtured and practiced in these tertiary institutes would be a very good indicator. The main question that begs to be answered is this: is there a necessity for capacity building at different levels, particularly grassroots levels? Is this question itself valid and worth discussing? Is also a question, is also what we had to look into today. This is the reason why we have this open floor or panel discussion. We want the experts in this panel to deliberate on issues and concerns ailing field hydrology in India, and in general how the science of hydrology can be helped here. For the benefit of all the participants, the following issues and concerns in no specific order are brought up, and the list is in front of you as a presentation. As a PPT. I'll read them out for your convenience. The first point there that has been put up as an issue or concern, or you can also take it as a conjecture, there is a need for premier institutions of the country to mentor the smaller institutions in hydrological research. Second point, the issue, dedicated funding is required for hydrological research or field work with hydrologists sitting on selection panels. Third point that has been put up, curriculums on hydrology in the universities and technical colleges have been marginalized all over the country, and there is a palpable apathy towards hydrology, and specifically field hydrology. Answer is to have a steering body for deciding on hydrology curriculum in the country and to drive the study of hydrology. Can we go to the next slide, please? Yeah. The next point is, can tertiary research and technical institutes be helped with procuring cost-effective instrumentation and monitoring equipment? Should one of the premier institutions of the country, any one of the premier institutions of the country, work on developing indigenously and cost-effective hydrology instrumentation? The next point that we have that can be also deliberated on is high charges for the supply of hydrological data held or gathered by the different government departments and organizations is an issue with all the researchers face. Is it forming a bottleneck? Is the attitude penny wise pound foolish? This is also to be deliberated. The last point that I have put up, in case of field hydrology specifically, is there no special recognition and encouragement for field work in the system, such as in jobs, publishing of papers, funding, etc. So this should provide the setting for the experts to start a discussion today. Let's go on to the experts. I would like to invite Dr. Lakshman Nandagiri to start the discussion. Sir, you all the panelists or the experts that we have, the 4 experts, we have thought of giving 5 minutes for each of the experts. So you have 5 minutes to present your opinion and suggestions, sir. Please.
Yeah, thank you, Professor Javed. Good evening to all the participants and my co-panelists on this open floor discussion. At the almost the fag end of this very interesting international workshop on field hydrology research. I completely agree with all the points which were raised by Professor Javed in his presentation, and I would like to only re-emphasize some of the points that he has raised. In my own experience, if you look at the curriculum in hydrology, I think hardly any effort has been made to come out with a uniform state-of-art curriculum which should exist at the undergraduate level, which is probably a little difficult, but more easy at the postgraduate level. At the MTech level, we can all think of having a common curriculum. I did some research on this hydrology curriculum last year, and I found that the UNESCO took up this issue very seriously during the International Hydrological Decade, and in 1974 they published a document which is available on the internet, and I can share it with anybody who is interested. And then in 1983 they came out with another document on what should be the model curriculum for hydrology at the postgraduate level. And after that, I don't think there has been any effort, neither at the international level nor at the national level, in coming out with some kind of a structured curriculum for postgraduate education at least. So last year I happened to speak to Dr. Sharad Jain, who was then heading the National Institute of Hydrology, Roorkee. I am a member in their regional coordination committee, so I happened to meet him and I raised this issue with him in the meeting. And he was quite receptive to this idea. I told him, sir, you have an international hydrology program, IHP, which has been running for more than 10, 20 years now, with a lot of funding which is coming from the World Bank and many other organizations. And I told him, how much money are you going to give for hydrology education out of the crores that you have got? He laughed and he said, sorry, Professor Nandagiri, we don't have any money for hydrology education, but we have a lot of money for hydrology training. I said, sir, training is different, education is different. Training is something that happens to working professionals who are already in the state departments and central departments who work in hydrology. You provide them training, that is different. But your potential hydrologists exist in the technical institutions and universities. So we need to train them properly at the level of education so that you don't have to provide that additional training later. So he was quite receptive to it. And last year they had a workshop in NIH Roorkee in commemoration of their Golden Jubilee or Diamond Jubilee, I forget. And there was one panel discussion, but unfortunately I could not attend that panel discussion. So the point that I'm trying to make is that, yes, we have all been talking about this curriculum, but nothing has come out of it. So I sincerely believe that all of us should sit together. I am prepared to be a part of any effort where we can come out with a curriculum at least for the postgraduate studies. Yeah, because I know it's very difficult to implement at the undergraduate level because each institution has a different number of subjects allocated for hydrology and water resources. So it may be difficult. But for at least the postgraduate programs of water resources, I think we should come out with a model curriculum. And there is a urgent need for creating this kind of a document. And we can only suggest. I don't think anybody can force an institution to adopt that curriculum. We can only recommend that this is the curriculum that should be adopted. The second issue which I would like to talk about is the research aspect. And here, if you look at it finally, who does the hydrology research? Actually, if you look at it, who is doing the research? I don't think we are all doing the real research. We are not the people doing the research. The research is being done by the students, especially the postgraduate students and the PhD students. And whenever I allot a thesis topic either to an MTech student or a PhD student, there is a lot of, they are concerned about how relevant it is, whether it will be useful for getting them a job. This is how they look at it. We may be very keen on offering them something in field hydrology, but their perspective is different. They are looking at it from a more, viewpoint where they are looking at their future and whether they can get employment. So I think we should also keep that in mind when we talk about, especially at the postgraduate level, when we talk about the kind of research topics that we offer. And one other point which I'd like to make is in this program, in this workshop, I may be wrong, please correct me if I'm wrong, but I don't think there was much focus on field measurements in urban hydrology. I think that is also equally important because urban hydrology is becoming more important in our country than hill slope hydrology, I think, because of the kind of urbanization that is happening and the kind of problems, water-related problems that we are facing. So urban hydrology field research is something that can be very attractive to students because ultimately, if he does something on urban hydrology, urban storm drainage, measurements and all that, he has a better chance of getting into a consulting firm with an employment. So I think we should also keep our minds open to other areas, other sub-branches in hydrology and not think that field hydrology should focus only on hill slope hydrology or on only agricultural hydrology, but also there are other areas which we should try to bring in. In this context, I also feel all of us who are interested and passionate about field hydrology, we can all sit together and try to come out with a manual on field hydrological procedures. I think it's very important. Students will find it very useful. And I am prepared to contribute in whatever way possible in making this manual happen, especially for postgraduate and PhD students. And today we don't even have to bother about publishing the book. We can have an online edition which can be available. Students enjoy the online version more than a printed version. So a manual on field hydrology and procedures. I remember using a book by a person called Trout, Manual on Field Procedures. When I did my PhD, I remember using that book. After that, I have not seen any book on procedures of field hydrological research. So we can think of that. And the point about the funding which Professor Javed raised, I think if not directly, indirectly, I think each one of us can promote measurements by students as reviewers. When we sit as reviewers for project proposals, or we sit as reviewers for journal papers, or we review even PhD thesis and MTech thesis, I think we should start asking, where are the measurements? What measurements have you made? Without the measurements, we will not accept your thesis. We will not accept your paper. Show us some measurements. So indirectly, I think we need to put pressure on both the student community as well as the supervisors and make them realize that their papers will not get published if there are no measurements available. Their projects will not be sanctioned if measurements are not part of it. So I think an indirect way is possible if each one of us wants to do it. And also the other problem in hydrology, unlike the other disciplines of civil engineering, is that in civil engineering, other disciplines, you can have laboratory experiments. and students enjoy that because it's very convenient to go into the lab and do a concrete lab or a soil mechanics lab or some lab experiments can be done. Unfortunately, in hydrology, we don't have field laboratories. So I think we must seriously make efforts to bring the field, a part of the field, into our labs and give them an exposure. Maybe our own campuses can be used. I know IIT Guwahati has experimental watersheds. I think campuses which have some large area can create small, patches where students can go out and do experiments. Because if you tell them you go to the Western Ghats, you go into the Himalayas for measurements, they may not find it very attractive because they are worried about eating, sleeping, air-conditioned room. You have to realize those comforts. So why don't we start off in our own campuses with small experiments and then try to move forward? And the point that I was discussing just before the discussion happened, that we need a directory of hydrologists in the country and also maybe from outside the country, one document which will be available for all of us to use, and with a brief description of the area of expertise for each one of them and their contact details, so that we can contact them and network with interested people. I think that's very important. And finally, I don't know if I have overshot my time, Dr. Javed. Just last point. Yeah, last point. I have been part of the International Association for Hydrological Sciences Decadal Initiative. And I was part of the Decadal Initiative on prediction in ungauged basins, which happened from 2002 to 2012. And from 2012 till now, 2022, currently there is an initiative called PANTA-RAY, which is basically about change assessment in hydrology. So I think the next hydrological decade should be on field hydrology. So let us all try to convince people who have some influence in IHS that the next hydrological decade should be on field hydrology research. I think Jeffrey has a lot of influence in the International Association for Hydrological Sciences. I can talk to Dr. Murugeshu Sivapalan. We can talk to Professor VP Singh. Whomever we can talk to, let us from India, let us push for international decade on field hydrology from the International Association for Hydrological Sciences. Thank you very much.
Professor Nandgiri, thank you. I think we are short of time now. The important point is we have Professor McDonnell who's going to come online, I think exactly at 5:30, so that I'm a little worried about that. I'm sorry, if not, we could have had more of time. Now, Dr. Devapriya Datta is online, so welcome. And I introduced you to the participants earlier to your arrival. And then we also have Shri Kirit Kumar with us, if I'm right. So I also would like to welcome him. I would like to invite Dr. Ruiz to give his opinion and suggestions. Sir, please, can we have it just for about 5 minutes? Because we'll be coming back once more.
I'll be very short, don't worry. So I must say I agree with most of the point that Professor Dr. Lashman pointed out. I am not very well aware about the curriculum aspect of the question. But to make very short points, I think yes, no doubt, doing field work is very interesting. It's a very nice exercise, but it's not rewarding. And this is true all over the world. Like, of course, if you take a bunch of global data from several satellite images, etc., make some computing and nice fancy data mining approach and publish a paper, you will go to Nature or Science without any problem. But if you spend 2 years as a student in a PhD measuring discharge in the Western Ghats, luckily you'll publish in Current Science. Okay, so the thing is that, I mean, we cannot force papers and journals to accept work like that. Maybe what we could do as a community is to highlight the importance of the work we do. and why we need to understand processes, and for what. Like telling we want to understand transit time, or we want to understand what kind of process is governing the storm event. It's very interesting for us, but it's not appealing for the society. Sometimes as a community, we are too much self-centered. We believe that what is interesting for us will be interesting for everyone. It's not. So there are communities like climate science which have managed to get their field becoming very important in the societal discourse. And the climate change, today it's a very hot field. We know that climate change is very important, but we know that hydrological change is also very important. But we have not been able as a community to alert people and to show them that by understanding processes, they will make better decisions, take better management, and all this kind of thing. So if you want to, you have to attract not only students, but also have a voice where funding agency, policymaker, and the society will understand what we are doing and for what, for the benefit of whom. So we should probably open up. Well, and about funding, actually funding has been difficult in all fields in research nowadays. It's something quite competitive. I agree that many times the disciplines are not really well represented in the course, but it's again the same problem. It's because the subject we are pushing. So there is some interference. The problem we are pushing are not really well advertised at several levels, especially toward the society. So that will be my short point. And Youssef, you are mute.
Thank you, Dr. Ruiz, for your very short but very important opinion. And then we would like to move ahead with, I would like to invite Shri Kirit Kumar, Mission Director, National Mission on Hydrological Studies, to deliberate and also to give his opinion.
I am audible?
Yes, sir, you are audible. Sir, you have about 5 minutes to...
yeah, no, I will not take that much time. I have few points.
Yes,
I have few points to make here because presently when we talk about the field hydrology and in the context of India or particularly this region, this Himalaya is the, we cannot exclude that actually. This is the most important, I think, region where the field hydrology is very critical issue. And as we all know that Himalaya, we have very limited data available for hydrology, not only hydrology, but other fields also. But hydrology also is a really, we suffer a lot because in our country, if you know, we have a system of some institutions collecting data, hydrological data as well as meteorological data. Central Water Commission is there, which is responsible for collecting the hydrological data for the rivers, particularly the big rivers. And similarly, we have meteorological department. But when we talk about the regional differences, you see Himalayan region is not well represented in that also. So why this problem is? This problem is because the field hydrology is really a difficult subject. And when we talk about going to the field in Himalayan region or any mountainous region particularly, so the challenge becomes even more. So what I would like to submit here, because this is the session for field hydrology future, how we can go about it. So in my opinion, there are 2-3 issues which may consider. The first issue comes is whether the collection of data itself is very difficult, so how, and very costly affair. So resources is the first issue. Where are the resources available for going for the field and collecting the information from the field? So is there any program, is there any dedicated program for field hydrology, not only in our country, but maybe in other countries also? That should be there. Second point, important point comes is in our conditions, as we all know that we work on the project mode. So project board means it is normally 3-year, 5-year project. So whatever we generate from the project in terms of field hydrological monitoring, so it is hardly any long-term monitoring available there. We do a small experiments in different areas, collect some data for 1 year, 2 year, and then we move to the other area. Or the instruments are mostly become non-functional. So this is another challenge, how to make a continuous data collection in the field hydrology site. So that will be the second point, which I feel that there should be a dedicated system or something, some arrangement, institutional arrangement for continuing data, long-term monitoring, which we call, which is very critical for the hydrological science. And then the third point comes of in my mind is of capacity, which is also highlighted in the points which are raised for the session. I also feel that there is a big gap in the capacity of data collection. The workers in the field, they have very little information about the latest technologies and latest methods and tools even. So there is a need for making a bridging courses where the field hydrologists can be trained in the latest technologies. So this gap which is there actually, if you see the people working on the computers, models, or collecting data through the available sources like international data bank is there for several things. I feel there is a need for making a bridge between these two. One which is collecting the data in the field. This is a really difficult task. And then second is who is doing the modeling part or who is doing the analysis part in the lab. That is equally important, but that is little easier than what I feel in the field. So these 3 points I would like to submit here. I will not take much time here because this is a long panel there. So thank you, Dr. Subhasis Dattaji, for calling me. And as far as NMHS is concerned, we are supporting water hydrological projects in the mission. And so far we have given around 20 such projects in the Himalayan region, different states, who are collecting data. So our worry is also the same, how this data bank can be made available to the people who can work on the data, but how simultaneously how we can continue with the collection of data in future also. So these are my submissions, sir, at this stage. Thank you very much.
Thank you, Shri Kirit Kumar, sir. Let's go on, and I would like to invite Dr. Debapriya Datta to deliberate and also to give his opinion on the matter.
Good evening, Dr. Javed and Dr. Subhasis Datta. Can you hear me?
Yes, I can hear you. Yes, you are audible.
So I think the focus is here on the future of field hydrology, and actually, if you see in any of the field-based science, whether it is hydrology and geology, where the first, the speaker, professor, I'm forgetting his name, I'm sorry for that, raised the issue because the total societal learning process has changed, because no students now want to go to the field because everyone wants to have a simulation and modeling, that is the focus itself. Now you look at it from the societal perspective, and we, I come from the Department of Science and Technology, Government of India, so I can give a little bit of the, funding agency perspective also, which is the government perspective. If you see the overall, the focus is here, the more on the knowledge converting into the actions on the field, and I believe that is the evolutionary pathway of also the research itself. I remember Dr. Subhasis knows in '98 in DST I started a network program on hydrology of the small watersheds. Then subsequently we work on the hydrological information systems. Then recently we worked on more towards an application side of the network of the the water bodies, the water bodies of the Indias and their hydrological things. And now we are working on a GRACE program supporting. But the focus is continuously going on towards these solutions. And in the process, we are really following, forgetting the worth of the knowledge generations, because you cannot make a solutions unless this knowledge part is very strong. So I was just now looking into that who in the country are supposed to invest into this, because all the investment from the government, what is looking about towards an immediate and short-term return. which is not possible from the knowledge to these, these conversions. So for these, the community, like from the hydrological research community, has to impress, have a dialogue with the government that definitely the solution-centric research is important, but the knowledge-centric research is also important. And now to attract the next generations, I think even these knowledge-centric research has to have an the root into the real problems, because the professor is right, spoke first, that these generations is looking for the immediate return. Not enough our generations, we thought about the long term career and these things. They are looking for an immediate the return, and that is the societal change what has taken place. What the value they will find, that their knowledge which can bring the immediate value or the market in that, because they are in a much more market best society than what we are. So that these are the factors we need to the built in while evolving the curriculum of hydrology. And now the field hydrology, I think that terminology also probably the community should think that whether the term field hydrology you should use, or you should use some other terminology which gives you more of a solution set. On my right hand side, I am just now coming from a one of the web clinic we are running here for linking the science and society. On my right, I became late because of that. Here the society is talking about the problems, and on the other hand, what we see is the and generating the knowledge. And in the context of our country, as you know, that the more focus the government is giving on the self-sufficiency, we find a big systemic gap here. Please keep that in mind while evolving our the curriculum, because until we can create a value of the of the knowledge, what a curriculum is, it will become obsolete of that type of knowledge, or it will lose the context. So I just bring on the table, please keep these things in mind while evolving your sectors. And I think the time has come now, we must look beyond that, the community of the researchers, because when the moment you say the community of the researchers, we go into that silos, and the time has come to look beyond the silos. And the day before yesterday, I was we have a program for the landslide zone, landslide hazard mitigations. I was looking into this, the landslide hazard zonations, that community, their language is different. But if you see the physical processes, they have a strong link with the hydrological processes, with the otherwise the water resource community would have. I suggested that, when you are looking into this landslide as a developmental process, please consider also the watershed integrated into that. So we have to, while developing, this is a difficult and, balancing between the practicality and the the openness of the knowledge, because the openness of the knowledge and the practicality should have an the optimizations for developing any type of a future pathway for development of any knowledge sectors in today's world. So this is my suggestions, and I hope this view have some value, because I am looking it from the point of view of the governmental or the the funding agency perspective. Thank you very much.
Thank you, sir. According to our plan, we should be opening the session for question and answers from the participants. I think we'll have a fast job of that, and we will open the session for 10 minutes to the participants to raise their questions and also to give suggestions. Please, Professor Datta, can you manage the question and answers from your side? Professor Datta, can you manage the question and answers from your side?
Yes, just.
Please, sir.
Good afternoon to all, and as well as good morning to Professor McDonnell. He's there now. The first question is, what is that, sir? In today's time, most students want to go in software industry rather than the field. What are your thoughts on that? what should be the student do? I think this questions to Professor Nandagiri.
Oh, you are throwing the difficult ones at me? Okay. Yeah, I don't know, because see, ultimately, as I said in my remarks, I think the student's perspective is quite different from what we researchers think about hydrology. They are more thinking about bread and butter issues, and especially in such testing times where jobs are becoming more difficult in the core sectors of civil engineering, and the main employer for civil engineers in our country even today continues to be the government, either the central government or the state government. So it is not surprising to find that most of my undergraduate students end up in either software or financial analysis or stock markets or something like that, rather than in hydrology. So I think the solution can come only when the employment opportunities open up in the domain of civil engineering, and specifically in the domain of water resources and hydraulics engineering. And I see that happening over the last 2 years, because several of my postgraduate students are getting into consulting firms, because there is a renewed effort now, especially with the smart cities mission which has been launched by the government of India. I think more and more urban bodies are employing civil engineering graduates, and especially postgraduates with specialization in hydraulics and water resources engineering. So I think the future looks good. The past has been quite bleak, but the future looks good for hydrology in India.
Yeah, Professor Datta, just can I supplement it, like, because, just on the other side of this meeting, there is we are, the joint secretary from the Ministry of SME is sitting here. Just now we are discussing about they have a target of 180 Spurti, the sectors. And these are all about the indigenous, the innovation, support and experiment. They want to work with the Department of Science and Technology, and where the hydrological instrumentations, one of the points what you have highlighted here, because in the country, you do not need the computer, the programming, but also you need the hydrological, the instruments, the sensors. This is a big opportunity for the students, especially from the IITs. And, there is a very good ecosystem for that to take it. So you have to open to the students for this type of a new knowledge-based, the opportunities, and definitely they will be interested in that.
Yes, Professor Javed, you can continue. There is no questions from me.
If there are no questions, I think what we can do is, after the experts having heard each other's opinion, if they have anything more to add or want to deliberate, we'll have one more round, very fast round, with each expert given about 2 minutes. Shall we do that, Professor Datta? We'll go.
Yes, we can do it. And Professor McDonnell is there. You can request him for just briefing about what the situation in USA and this, whether really field research, hydrology.
I hope.
So you can request Professor McDonnell.
Professor McDonnell, I just want to apprise you what we are doing here now. This session was given 1 hour. In this session, the title of the theme of the session was Road Ahead for Field Hydrology Issues and Concerns. And now, Professor Datta, can we bring up those 2 slides that we had put up earlier? That will immediately orient Professor McDonnell to what we are deliberating here.
Yes, we are just. Yes, it is now.
Yes, Professor McDonnell, this is what we have been. These points were put up to anchor the thoughts of the people, to set the ball rolling for us today. Okay, so some of them are issues, some of them are concerns, some of them are conjectures. Okay, but anyway, the point was to set the ball rolling. Let me read them very fast for you. There is a need for premier institutions of the country to mentor smaller institutions in hydrological research. We have thousands of institutions here and colleges here. India is a big country. Keeping that in mind, the first point was put up. Second point is dedicated funding is required for hydrological research, fieldwork with hydrologists sitting on selection panels. Exclusive funding for hydrological research in the country. If not, we have general funding. Point number 3, curriculums in hydrology in universities and technical colleges has to be improved and made more, rather they have to address the present needs of the country. That was the point. Can we go to the next slide, please? Next, okay. The other important point was, can tertiary research and technical institutes be helped with procuring effective instrumentation and monitoring equipment? Should one of the premier institutions of the country, any one of the premier institutions of the country, work on developing indigenous instruments and cost-effective hydrology instrumentation? That's the point here. Personally, I have had problems. Okay, each instrument costs us about 70,000, 1 lakh rupees. The point, can we construct the same instrument spending about 1,500, 2,000 rupees? The point here, so that we can flood the catchments with a lot of instrumentation. Next point, high charges for the supply of hydrological data gathered by the different government organizations is an issue with all the researchers in India. Is it forming a bottleneck for research in India? Now, is the government penny wise, pound foolish? That's the point here. The next point is, in case of field hydrology specifically, is there no special recognition and encouragement for field work in the system, such as jobs, publishing of papers, funding, etc.? This is not an exhaustive list. It was a limited list. It was prepared to set the ball rolling. Once I think Professor McDonnell's prize, now he can give his opinion now, Professor Datta. Professor McDonnell, I'd like to invite you to this deliberation.
Some mutes. Professor McDonnell, please unmute.
Sorry, can you hear me now?
Yeah. Yes.
Okay, great. Yeah, well, it's a really interesting discussion, and I was able to sit in on part of it over the last 40 minutes or so as I was getting connected. I think there are some examples out there you might consider that addresses this issue of coordinating the community, sharing instrumentation, coming up with standardized teaching methods, particularly at the graduate level. And there's a group in the United States, but it's much bigger than that. Many countries in Europe and elsewhere are involved, called COASI. COASI is a long acronym for the Consortium of Universities for the Advancement of Hydrological Sciences Incorporated. So it's a terribly long name and a crazy acronym. But if you Google that, and I'll show it in my presentation shortly, they've developed standardized curriculum. They've developed shareable free data, not just within the US, but globally, as people upload to their COASI site. And that is a model that we in Canada and other groups I work with are trying to emulate. So that's something I'd point you towards. And I think it's many of the same issues that you've surfaced that countries around the world are grappling with. I think one last thing I'll maybe mention is that what's happened in Europe is a lot of short courses that are now offered to kind of compensate for the lack of a true graduate degree in hydrology. And I'll make reference to one of those, but I think that's increasingly a way to provide education, training, whatever you want to call it, at the graduate level. And probably it would be done in country in India, but you can bring a lot of people together, either virtually or physically, and give them the tools they need, particularly focused on field work, to then go and be disciples of that kind of approach.
Yes, Professor.
Thank you, Professor McDonnell, for your contribution. I think we are running out of time now. I'll maybe very fast conclude. Most of you were hearing the deliberation, so there's no point in what you call again repeating whatever the experts here have contributed.
Professor Javed?
Yes, sir.
I have just one point, if you don't mind. Just one, speak 1 second, because I just wanted to put this forward to Jeff. Jeff, one of the suggestions that I made to promote field hydrology research is that we have had the IHS decadal initiatives, one on Pub and now Panterei. So do you think it would be possible for us to push for the next decade to be on field hydrology?
Man, that's a great idea. I'd be behind that 100%.
Yes.
Yeah.
Yeah. So I think we should all come together and try to push for that.
Yeah.
And you can be our champion for the cause.
I'll be a cheerleader. How about that?
Javed?
Yes.
I have a small suggestion.
Yeah.
I have a small suggestion. Can all these be made into a set of recommendations and forwarded, submitted to some agency?
Yeah, I'll come to that. Okay. Yeah. Now, before I come to what Dr. Putti suggests now, I expected some deliberation on these 3 important points. You had the list with you, but let me read them out. Okay. There's a need for premier institutions to take the smaller institutions under their umbrella. I'm talking from Indian context point of view. I hope I think this plays a very important role if the small institutions in the country are mentored, fostered by the premier institutions. Okay. Now, accessing data is quite difficult in India. You have to pay huge amounts of money, and then project money is also very difficult to get, and so this is becoming a constraint. Okay, now the government is spending thousands of crores on a project to get data, and once the data is brought in, for small pittance, small monies, this data is being held back from the real users, the smaller institutions. Okay, I think this stranglehold should be removed. This bottleneck should be removed so that data is freely accessible to people. You charge money. Let's say you have a satellite mission costing 1,000 crores of rupees, and tell me how much of money you are getting by charging small poor institutions hardly 1 crore rupees. Now, how do you justify a big project when small monies are becoming a bottleneck? That was a point that had to be brought up. I think this has to be carefully looked into, and so this stranglehold and bottleneck has to be immediately removed. And one more thing that I wanted to have was instrumentation is damn expensive, very, very expensive. Now, I think it is very, as Dr. Debapriya Datta brought to our notice, I think we need to have smaller committees to take care of each one of these issues. Okay, and particularly developing indigenous instrumentation should be a priority from now on, so that you can promote field hydrology. I think it's good to talk practical solutions from now on than talking in a little philosophical way. That is what I wanted to say. Now, lastly, this is a lot of what you call expectation from this group, and as Dr. Putti was saying to us, we will write down all this as recommendations, and then we will circulate this recommendation, the draft of this recommendation, among the experts and also the other people connected with this discussion, and finally it would be submitted to the right people in the government. So I also seek your permissions to bring in your recommendations, your suggestions and deliberations into these recommendations. Is it fine, Dr. Datta?
Yes. Yeah, it's okay. This is okay. I think it's fine. It's fine.
So fine, sir. Now, I think with this concluding remarks of mine, we will bring this session to an end, because I think we are encroaching into the time of Professor McDonnell's now. I would like to once more thank all the people on this panel, the experts on this panel for their time that they have given us and for having accepted our invitation. Over to Professor Datta for the next session. Thank you, sir. Yeah. Thank you all.
Thank you, Professor David. So let me, I don't have to delay much. I think Professor McDonnell here, and it's a quite pleasure to us, almost the undergraduates and postgraduates, the research scholars, they have been waiting for you. So that's really, it's a quite interesting lecture what you delivered in the first day, and you want to conclude today with this lectures. Looking that, I just give a very brief CV. I think it's a 2-short CV for Professor McDonnell. So he's a professor of hydrology and associate editor of Global Institute for Water Security at the University of Saskatchewan. Before returning to Canada in year 2012, he was there as a Richardson Chair in Watershed Science in Oregon State University, the university distribution professors. Over this past 30 years, he has been working on the field-based runoff processes, description around the world, leading to new measurements, techniques, and a new understanding of dominated controls of rainfall runoff behaviors. He is the author of close to 300 papers and co-edited Elsewhere's text, Isotopes, Tracers, and Catchment Hydrology. Today we'll hear the lecture from that. Not only that, I don't want to take much time, and there are a bit lengthy this part. So I just to tell you some of the really this award part, what he has got as the president of the AGU hydrology sections and served as the president of IHS International Commission on Tracers. He is currently visiting chair in water science at the University of Buckingham, and this is a visiting professor in Tsinghua University, Beijing, Forestry University, Ludong University in China, where he focused on early career mentoring. I think that's quite interesting. With these few words, I just request Professor McDonnell to start his lecture.
Thank you very much. Thank you for that kind introduction. Can you see my screen? Are my slides showing?
Yeah, yes.
Okay, great. And they're advancing okay if I just double check before I get going here. That's okay, you can see them changing?
Yes.
Okay, great. Well, thanks again. It's great to be with you, and I've enjoyed the discussion this morning. What I'd like to do in this final lecture is talk about one field technique that's become very popular in hydrology in the last 20 years or so. And this builds on some things that I mentioned on Monday. And this technique, of course, is isotope tracers and their use in catchment hydrology. On Monday, we talked about the time evolution from the first field studies in hill slope hydrology in the 1930s to this all-important first international hydrological decade in the 1960s, when about 9,000 catchments were gauged around the world. And then the introduction and use of isotopes starting in roughly the mid-70s or so. But I would say that this tool, the stable isotope tracing tool, has become very commonplace in watersheds that are natural, disturbed, urban, agriculture. This is a tool that is not specific to any one land use. So I heard mention of a need to do more field hydrology in urban settings. This is being done in urban settings as well. And I'll hopefully tell you why it's been popular and how these field approaches can be brought into your own research. And I'll do a bit of an introduction, and then I'll follow that with some discussion of aging or getting the age of the water, or what we call its mean transit time through our catchment systems. And then some new work in the last decade on how we can use these tracers to get at questions of where do plants get their water. And of course, this is a key part of the hydrologic cycle for all of our systems. And in some environments in India, this can far exceed the flow in the stream in terms of the water cycling at the catchment scale. And then I'll talk about maybe the road ahead for field hydrology. So I expect to talk for about 45 minutes or so, if that's okay. All right, so just building on what I mentioned a few minutes ago, there are educational groups out there. This is one I'd encourage you to have a look at, the Kawazi. Again, if you just type that into your Google browser, it will come up. And not only are they putting educational material together, they're also a repository for hydrological instrumentation that they disseminate freely to their membership. So while you might not be able to have things shipped from the United States to India, you could come up with a kind of instrument sharing program modeled or fashioned on this kind of idea that is linked to Kawazi. So I'd encourage you to reach out if you want an introduction to the executive director, Jared Bales. You can let me know and I can connect you to them. And it's really a good template to consider following. And then a bit of shameless self-promotion. I run a catchment science summer school together with many professors in Europe, in the UK each summer. We've had students from India participate. This is a catchment science summer school. It goes for 5 days. And of course, graduate students are very welcome. And we usually have about 30 or 40 per year that come and learn about catchment science from a field-based and modeling perspective. We try to do integration of those techniques. I'll come back to that at the end of the talk. And again, field-based, we're out in the uplands of Scotland or Wales or England and looking at how data is collected. Okay, so isotope tracers in catchment hydrology. You saw this Monday, and this is really revolutionized the field because what it's allowed is the easy sampling of the rainfall or snowmelt stable isotope composition on the left-hand side, and then we can sample in a stream the water during an event or during base flow when it's not raining. And this has been a wonderful tool to understand particle transport at the catchment scale. And on Monday, we talked about how that contrasts with the pressure wave propagation through the catchment as represented by the stream hydrograph. And this is something I want to talk about today in terms of field activities and how we can learn things from field work using stable isotopes that we could never learn from models alone. But let me tell you first a little bit about the technique. So questions about what is an isotope? Why are the inputs that you're seeing here in this cartoon so cyclical? What controls the spatial pattern of precipitation? Let's start with some basic questions along those lines. And of course, the first thing we need to recognize is that stable isotopes are part of the water molecule. We're talking about the isotope composition of oxygen or hydrogen. And just like the water cycle you see on the left-hand side, the right-hand side, we can actually sample and analyze the isotope composition, not only of the liquid, but now of the vapor. And this is oxygen 18 values here in a unit called per mil. And you can see now that we can actually trace the signature. So we're talking about tracking raindrops. Think of this as a fingerprinting technique. And this is natural in our systems throughout India, throughout Europe and elsewhere where we embrace these techniques. So this is the first thing. It's part of the water molecule and it's added naturally by rain and snowmelt events. So a few of the basics, as I said, part of the water molecule, added naturally during events. They're conservative tracers. So unlike looking at, say, chloride in rainfall in your Western Ghats catchments, where you get a reaction along a flow path between a geochemical tracer and perhaps the soil or the saprolite that it's flowing through, These are conservative, and it's only mixing of different waters that can alter the concentration. So that's why it's been such a powerful tracer and so popular for use in hydrology. Because of course we're tracing oxygen and hydrogen isotopes that make up the water molecule. And this is often how we think of it. We're using ocean water as our standard. So the per mil notation you see down here in the lower left, or parts per thousand, it's all reference to a standard, and this is a standard that's identified by the UN's International Atomic Energy Agency, and this is our reference for the samples we look at in our terrestrial sites in catchments. So imagine this is the Indian Ocean, and you have an air mass coming over the Western Ghats or onto the Indian subcontinent. What happens is that the isotope ratios, there's a kind of a distillation that happens, so that the vapor that is coming from the ocean water becomes lighter, depleted, more negative in its isotope composition. And here I'm referring to O18 and 2H, which has a name called deuterium. And these isotope values, then as they move on land, they start to get more negative, and that's because the heavier isotopes, the O18 in the rainfall, falls out. It's wrung out. It's almost like part of the orographic uplift process that you all know about. But you can see how the rainfall relative to the vapor from which it comes is following very predictable changes as things move on land. So there are a lot of papers and theory that describe these changes, and these patterns or these values follow very well-known patterns that are mapped globally and regionally. And I would I can make reference to some databases that could be very helpful for your work in India, where perhaps you don't have such a rich data source in terms of isotope tracers and precipitation, but there are global networks that you could use to regionalize that information for your particular area. Now, a lot of this comes down to something called fractionation. This is the sorting the heavy from the light. So when we look at changes of state, meaning going from liquid to vapor, or looking at the cloud going from vapor to liquid, what happens is this fractionation, the sorting of the light and heavy isotopes. And this is best thought of, I think, as distillation. I'm a big fan of Scottish whiskey. After my short course each year in the UK, I might tour a distillery with my wife, and it's the same idea. You have a distillation, a separation, as you maybe evaporate a liquid with some alcohol in it. The lighter alcohol evaporates and moves up the still, and then it condenses when things are cooled, and that's a way to separate water and alcohol. It's the same idea with these stable isotopes in precipitation. And they follow very predictable patterns. So if we have on the y-axis is O18, our tracer, and on the x-axis is residual water fraction. So let's say we have a full glass of water, and that's residual water fraction of 1. So you can see that we're only going to look at lines A and B. So line A is the liquid in the glass, and line B is the vapor immediately above that liquid. So what happens is that the liquid, as it begins to disappear, maybe I drink it or it evaporates, the residual fraction goes to 50%, and then when it's all gone, 0. But you can see how the vapor is tracking all the time in the same way, lockstep with the liquid from which it's coming. And if you go back to that diagram that I showed you, you can kind of see that in some of the values as we look at the change from ocean water to the initial vapor. And now look at those numbers, the vapor to the rainfall, and then the vapor continues inland. I'm looking at the diagram in the upper right, and then the water that precipitates from that cloud, all the time getting more negative. lighter as it goes on land. Now, we could spend many hours talking about these processes, and I know we don't have time for that, but I'd encourage you, if you're interested in this, to look into this background material in different ways or attend a short course. But let's talk about how we can use this information now to say something about the transit time of water through our catchments. And again, they could be forested, they could be urban, they could be agricultural, but this measure of how long it takes for water to get from application to the surface to the stream, this can be a very potent tool for evaluating models, rejecting model structures that don't conform with this ground truth, if you like. So what is transit time? Really, it's just the elapsed time of the water through the system. So from the input at the boundary, which would be the soil surface, to the output in the stream, that would be the output boundary. So it's simply input minus output. And we think of this in our catchment sense. Of course, the input is the rainfall, and then the output is the stream water. And what we're doing is taking all these complexities of the catchment and the hill slope flow paths that I talked about on Monday, and we're putting it into a function. In this case, we're calling it the transit time distribution function. This is simply a mathematical function that describes all of that flow path heterogeneity on the left-hand side that you see in the catchment. So this is at the simplest level what we're going to try and do now to calculate the mean transit time of water in the stream. And at the hill slope scale, you can kind of think of it almost as a advective dispersive flow. This is a lovely diagram by Jim Kirshner, just showing you, as you have an input, how that input gets smeared as you move down slope. So look at the upslope, you get this spike in input, and then the water moving down the slope is following this kind of distribution. This distribution then in blue gets smeared as you move down slope, and you have more inputs that are occurring at the mid slope. Now by the time you get to the base of the slope, now that blue is really smeared. The red is a little bit smeared, but then you have new inputs happening spatially on the catchment in that zone. And the upshot of that is that if you take the whole distribution, it looks like an exponential, that blue line on the right-hand side. So this is effectively that transit time distribution. So take that blue line that you see showing that kind of exponential, that would be the transit time distribution that we would use to turn the input into that lagged and damped output. Now it's lagged and damped because it's moving through that catchment. It's filtered. And that's the filtering is what we're after. Because if your catchment is filtering water in the order of months or a year, you've got a very different situation to a catchment that's maybe filtering it on the time scale of decades or centuries. Or even minutes or hours if maybe you're in a very responsive urban system. And this is a piece of information that can be very, very helpful. Okay, let's look at an example. We're going to go to a forested watershed. This happens to be in Oregon in the Northwest United States. Again, we've got this very familiar graphic now that you've seen. And now you understand how these different transit time distributions can arise. We're only going to look at an exponential, but you're seeing a whole bunch of different functions. And if you're an engineer, you'll recognize them. They have names. They could be two parallel linear reservoirs, could be a gamma function, could be a Dirac function. And these are the different functions. We're going to assume an exponential. So we pick the one, I don't know if you can see my mouse, but I'm kind of tracing that exponential from the previous slide. And we're doing convolution. So we're convolving the input in the upper left with that function to give us a best fit on the flow that we sample in the stream channel. And again, this all derives from field work. Here's an example. This is oxygen 18 on the y-axis in per mil. These green dots are water samples we've taken from a small stream in the diagram in the upper right. And then this faint gray line is our projection through those data using this exponential convolution model. So it's really a best fit. But what it gives you then is the mean of that distribution. And the mean of that distribution, of that exponential, in this case, with these data, is 2.2 years. So that would be the mean transit time of water moving through the catchment and appearing in the stream channel. So now we have a number that we can assign to a stream. Let's look at a whole bunch of streams. This is a well-instrumented watershed. Again, this is the site in Oregon. The outflow of the whole thing is about 60 square kilometers, and there are many small sub-watersheds within it. One question we might have is not only how old is the water, but does the water get older as we go to larger and larger catchment scales? We can ask that with our stable isotope tracing approach. So let's look at that. Here are a number of catchments. They vary in size. On the y-axis is the isotope composition of the stream water. And you can see the stream samples that we've collected are shown in these different colors. And we've done this convolution technique to calculate on the right-hand side these different ages, if you like, from just under a year to just over 3 years. So the question is, you don't know what these watersheds are, but they all are from this map. The first question in our minds was, well, does the water get older as you go to larger catchment scales? Because we might hypothesize in this volcanic landscape with very tight bedrock, these are breccias mostly that are very low permeability, but in this volcanic landscape, does water get older as we go to larger basin scales? And what we found was that the answer to that is no. If we look at mean transit time on the y-axis versus catchment area for these 8 catchments that we looked at that are ranging from about 10 hectares to about 60 square kilometers, what we found was no relationship with basin area. But what we did find was that if we take the same data, the mean transit time on the y-axis, and we look at the length of the slope and the gradients of the slopes that make up these watersheds, what we find is that we can explain about 90% of the variance with these topographic measures. So this was something that we learned about our system in terms of the way things scale and how things are processed, what we could not have learned with hydrograph analysis. I'll try to give you an example of why that is in just a minute. Now, the site that we just looked at is the small red circle in the upper right-hand corner. This is a Google image looking at Oregon. You see some of those volcanoes in the background. Now we're going to move into the foreground, and these are another set of 8 or so catchments, similar size range, but now the only thing that's different is we changed geology. Here we've gone to a more permeable rock, mudstones, and the like. So these are different rock types, but otherwise the rainfall is about the same. This is about 2,000 millimeters per year. These are steep, highly responsive catchments. I'll just show you that if we look at the hydrographs for these 2 sites, these 2 regions in that state of Oregon, this is what 4 years of flow data looks like for the first set of catchments we looked at. And this is what the hydrographs look like for these coast range catchments. Again, we're just looking at rainfall along the top and then flow in this rather seasonal environment, long dry summers, wet winters. And you can see that the rainfall runoff looks pretty similar. And if we dive in and look at this in log scale to really look at some of the differences, it's all much of a muchness. So despite the fact that the geology has changed, precipitation, slope angles, even the total amounts of rainfall are very similar. And looking in this area I've highlighted in red, you'd be hard pressed to see differences between the hydrographs in these 2 regions. So the hydrographs are very, very similar. Now, are the isotope patterns similar too in terms of the scaling of mean transit time? So let's look at that. The answer is shown in the bullet points above, and the punchline is that no, there is no. It's not similar when you look at the the mean transit time. Over here in this area in the Coast Range on the left side there, even though you have very similar hydrograph response, it's much older water. So remember, in the volcanic area, streams range from about 1 to 3 years old, and they scaled with topography. There was no relationship to area. Here it's the opposite. There was older water ranging from about 3 to 11 years old, and no relationship to topography, but area could explain about 80% of the variance of these catchments, the many catchments we gauged over here to compare to the other site. So what the isotopes are revealing are differences in cycling of water that we'd be blind to simply with rainfall runoff. And this is very helpful because it's telling us something that we didn't otherwise know. And we go to these areas in the Coast Range that have this alternating layers of mudstone, siltstone, more permeable geology, we can now see that geological effect expressing itself in the stream. And if you look at in this area where we saw these older waters that scaled with basin area, basically things are following much deeper, longer flow paths to the stream. So very different kind of system. And so field analysis of these samples that one can collect in your system can help to understand maybe differences like this. The one site, the first one we looked at in the volcanic area, things really get shunted laterally, follow topography, and the water is very young, 1 to 3 years old. In the Coast Range, more permeable bedrock, things are moving deeper, things aren't shunted laterally due to topography that's really affected by basin area. These are really two different types of sponges. So the hydrology is fundamentally different, but we would not have seen that with the hydrograph analysis that was pretty much the same in both cases. So this has really helped, I think, a lot of groups around the world understand how their landscapes are storing and releasing water, which is so fundamental to sustainable water management. The second example I want to give is plant water. Again, thinking about the catchment water balance, evapotranspiration is often a big component. In many areas, it's the largest component. Perhaps in the Western Ghats, it's not the largest component because you have just incredible amounts of rainfall and runoff. But as you get to areas that are less humid, this can be really a big number. And what I'm going to show you is that we can also trace the water in the plant and ask where the plant's getting its water. And what we've assumed up until recently is that the soil water, even though you have preferential flow paths and so on, the soil water is well mixed in the sense that the water that the trees are using is really water that perhaps didn't go to runoff or groundwater recharge, and vice versa. The water that goes to groundwater recharge or stream flow is water that got past the rooting zone. We're going to look at this and actually sample the water moving in the transpiration stream, just like we'd sample an actual stream, using the stable isotope approach. This has been done now for many decades. This was a paper in Nature in 1991 by Todd Dawson at Berkeley and Jim Elringer at University of Utah. And they looked at where trees get their water, what water is it. This is the 2H or deuterium composition of water they sampled in the xylem of the tree, this flowing zone of water that is moving through the trunk of the tree. And these were some really fascinating data because what they showed was on the x-axis you're seeing tree diameter, and for the small trees, if you kind of look at the band over to the isotope composition of precipitation, stream water, and groundwater, what you can see is those small trees are using largely precipitation. And then very quickly, as the trees get to a certain diameter, they switch over to, in this case, a groundwater source. Again, not something you could easily detect without extensive excavation or other measurements that the isotopes are telling you quite quickly and quite clearly. And up until about a decade ago, most of this work was done with one or the other isotope. And what we're going to do now, or talk about now with these stable isotopes, is how we can use them together. So again, you've seen this diagram on the bottom that's just flashed in, the sinusoidal input from different seasons of precipitation being kind of flattened when you look at the stream flow. And this is covering a period of about 6 or 7 years. It's more negative in the wintertime, more closer to zero in the summertime, these inputs. Well, we can look at that in dual isotope space, where we plot one isotope against the other, and now rather than that sine wave, it maps along a line, and that line we call the meteoric water line. So for instance, the high amplitude of precipitation, now it's stretching out along that line, and the sinusoidal nature is just moving up and down that line. And the damping and the lagging that you see in the base flow in that lower right-hand corner cartoon that you've seen many times now, there's the stream flow. It's now damped, but it's showing that damping as a compression along that meteoric water line. Now, in the catchments where I've worked, this is a Western Ghats-like catchment in Mexico. It's a very steep, very wet rainforest where we've been collecting water. All the waters that I'd looked at up until a few years ago, it stretched out along that line. And that rainfall, of course, had the biggest amplitude. And then as we go into the soil and stream and groundwater, things get more and more damped because you're mixing with larger and larger amounts of existing water. But anything that falls below that line is a telltale sign of evaporation. So going back to our glass of water, if we were in a very dry environment here and this was evaporating, the remaining water, if we took a sample, would no longer look like it was on the line, but it would plot below that line, showing the effects of that evaporative fractionation. Similarly, if we sampled water from a catchment in, I don't know, Hawaii that's raking in a lot of vapor in a cloud forest, and that vapor was condensing and falling to the forest floor, that condensed water would plot above the meteoric water line. So this is a way to partition or see if your sample has undergone additional fractionation, condensation, evaporation effects. Okay, back to Oregon. We're going to look at this 10-hectare catchment, and we're going to ask, where do the trees get their water, and can we use this tracing technique to get at them? And again, we're assuming that the trees are using the same water that we see in the stream or in our trench flow or come into our groundwater, and how can we understand that mixing and that removal of water by evapotranspiration? And these were some initial data that we collected. This is a colleague of mine, Renee Brooks, who's at the Environmental Protection Agency. And all of the data that I'd looked at prior to this collaboration with Renee fell along that meteoric water line. And one day she came to morning coffee with these green triangles. And these green triangles are her trees that she sampled in this diagram in the upper left. These are about 50-year-old Douglas fir trees. Here she'd sampled the xylem water, meaning taken some xylem tissue, extracted that water, and they plotted here below that meteoric water line. All of my soil water and all of the waters I'd sampled had fallen on that line. We then had to scratch our heads and say, where are the trees getting their water? So we resampled the soil, but this time used a technique called cryogenic extraction. Basically, it's a technique to get all the water out of the soil. And what we found, perhaps not surprisingly in hindsight, is that the trees are using that soil water. If you look at the open dots in the upper right, that's the shallowest soil water, the most evaporated. And then as you go deeper, 10, 20, 30, 40, it's following a very predictable pattern back to the meteoric water line. The trees are using water kind of from the middle area there. But they're trending on an evaporation line that we don't see in the stream water, in our more mobile soil water that we'd sample, let's say, with a suction lysimeter. So this is telling us that the trees are not using the same water we see in the stream, because the stream water and all the waters that relate to it are falling on that meteoric water line. This was a mystery. And it's saying that these two systems are not well mixed. The trees seem to be using one type of water, much more tightly bound water, and the mobile water seems to be following another slope on this dual isotope plot. And when we compare, for instance, the water that we pump from a suction lysimeter on the y-axis, these are porous cup devices that you vacuum down to, I don't know, 60 inches of mercury or so, and then you sample the vadose zone water, and compare that to these extractions, the so-called bulk water on the y-axis. This is that cryogenically extracted water. What we see in all of these samples is that the two pools are not mixing. This now is really a predicament, and the two pools are not mixing, and we were hard pressed to explain it. And this is what we came up with. And again, this is a picture of the catchment here in the upper right. It's a wet place, but it's seasonally dry. What we think is going on is that during the end of a long dry summer, on the left-hand side, diagram A, we get a rainfall event. And that rainfall event recharges these soil waters that have been really mined of their water by the vegetation through these few months of rain-free period. The rainfall recharges that kind of tightly bound water, and there are aspects to that rainfall that we talked about just a little bit at the beginning of the lecture in terms of the squeezing out and the rain out effects. But what happens is that it's followed by a long rainy season of, where the 2,500 or so millimeters of precipitation comes in, but that rainfall doesn't seem to be mixing with that tightly bound water. And then 6 months later, in the dry season, when the trees wake up and start transpiring, they're using that water that was recharged 6 months earlier. We called this eco-hydrological separation. Now, we didn't believe it, so we wanted to see how widespread this would be. And this is some work led by a former PhD student who's now a professor at Utrecht University, Havame Ivaristo. And we went and identified about 50 studies we could find in the literature that had the dual isotope data, had precipitation data, and had sap flow data or xylem data where we could test this hypothesis. And again, we posed it as a null hypothesis to try and reject, because we were thinking that these findings maybe were unique to this site in Oregon. And what we found was that it wasn't unique. And in fact, if we look at this kind of global data set, if I can call it that, there's since been much more research published in the last 5 years. Again, looking at these dual isotope plots, just as we'd expect, groundwater, stream water, rainfall falls on that meteoric water line. But the plant water and the soil water, again, soil water extracted by this cryogenic extraction technique, is falling below the line, saying that there are these kind of separate water worlds, as it were, in terms of the tree uptake and the mobile uptake, a kind of a partitioning between these two types of systems. And maybe in cartoon form, this is what I'm saying. On the left-hand side, we have the familiar now meteoric water line with the lagging and damping of the stream, just like we saw in the sinusoidal patterns. Now in dual isotope space, that damping expresses itself as shown in yellow. On the right-hand side, this is the way it looks, it seems, for the soil water. Again, soil water stretching out along now an evaporation line, and the plants are a lagged and damp version of this. So this is an active area of research, field research, and again, the isotopes are showing us things that we would not have been able to see easily otherwise. All right, so I'd like to segue now to kind of a wrap up and maybe the road ahead for field hydrology. What I'm saying is that we've come a long way, I think, as a community, and these are some of the key points in time, as we talked about on Monday, and we're still impacted by the use of stable isotopes in our systems. as a way to complement other things we're doing with our field-based studies. So I don't want to leave the impression that just use isotopes and everything will be wonderful. You need to use them in concert with other hydrometric standard techniques. But what the isotopes have shown is that most hydrographs are dominated by pre-event water. There's a lot of different release mechanisms, but as we talked about on Monday, they all seem to be some sort of filling and spilling. I think you've seen that in terms of isotopes versus the traditional rainfall runoff data, catchments are transmitting their so-called hydraulic potentials differently than they transmit the water itself. This is the difference between, say, celerity and velocity, as we talked about on Monday. And things like topography, soils, geology control this, and our job as field hydrologists is to understand that, to compare and contrast and classify these behaviors. And I think, boy, if we could do that going forward, that will really help. These field studies that we could do in different environments in India and other environments could enable us to come up with a typology of hill slopes or catchments to understand how development intensity influences some of these factors. I think that would really be helpful. And of course, our questions for our field studies are, again, where does the water come from? How long does it take to get into the stream? What's the flow path of water? The source, flow path, and transit time. Because these are the key elements of our model structures that we might be using in prediction. And if we are just somehow assuming a one-size-fits-all model structure, I think we realize from our field studies that, you know, all catchments are unique in some way. Our goal is to somehow understand that uniqueness and perhaps group them into different bins. So this is like diagnosis, as a medical doctor would do. You go to a doctor and he or she sees you, you know, they take your blood pressure, your temperature, maybe your heart rate. They don't just automatically assume without any measurements that you have a particular ailment. It's the same thing, I think, in terms of hydrology. The field data collection is necessary to understand what the diagnosis might be for the type of model structure that could be used or the type of system you're dealing with. And don't forget that there's so much we don't understand about our systems. It's so easy to lead from, again, a Darcy-Richards or St. Venant equation and almost mask our uncertainty about natural conditions with these equations that really are not capturing fully the complexity of our landscapes. And I think that's another reason why field measurements are so useful. And this is a lovely paper by a group in Switzerland led by Ilya van Meerveld at Zurich that I love to show. It's just such a compelling visual on a Swiss hill slope. And going back to Monday, I think one of our challenges in the field as well is understanding how landscapes connect and disconnect. I showed this at the hill slope scale on Monday, but it also relates to the larger catchment. This idea that catchments are very operating almost like cryptic reservoirs that connect and disconnect in very threshold-like ways. Our job as field scientists, I think, is to understand when, how, why things get connected. And using field techniques like trenching, distributed groundwater measurements, tracer experiments, geophysical measurements to maybe diagnose and get at some of these connections that we might see. And our big challenge is not only this that I showed you on Monday, trying to understand, you know, where the water is coming from in time and space that makes up the storm hydrograph, but with what I showed you today with transit time, we're also needing to understand where the water is coming from depth-wise in the system. And that example I showed illustrated how in certain geological environments, you can really activate deeper, older water. And this can really change the processing of your landscape to anthropogenic inputs, for instance, like nitrate or other contaminants. And maybe just one or two last comments. If you have interests in some of these techniques, I showed you just one very simple approach for getting at transit time. This too has exploded in the last 5 years or so, and there's been some very healthy dialogue between experimentalists and numerical modelers coming up with a whole host of new approaches to characterizing mean transit time. And this is a very exciting field. Particle tracking models, trying to do this within hydrologic models and so on. So this is also another area where papers are coming out weekly with these new techniques and approaches. And then lastly, I guess going back to the comments at the beginning of this session, we really need to counter this trend that I talked about on Monday, where if we look on the y-axis at percentage of papers published since Horton's work in the 30s, it's really kind of a sad state of affairs where field-based papers are declining, where model-based papers are continuing to rise quite quickly. It's not that models are bad or not useful. I think it's just that we need a healthy dialogue between experimentalist and modeler, and this is something I think this session and this whole week has really been a great celebration of field work, and I look forward to more discussions if there's time remaining. So thanks very much.
Thank you, Professor McDonnell, for these nice presentations and highlighting many things which is really interesting. Talking about there is two separate platform, plant waters and stream waters. So I think many more things to be done in this field, as well as you said it correctly, that now we should look for particle tracking in hydrology system. It's not only the output of the hydrographs, which always we look at from, and very nicely you put it, two hydrographs are the same, but travel times are not that. So that's the really interesting things. I just want to have a few questions from my panels, and I'll look at the questions from also the participants. So anybody from panels? Yes, any questions from panel?
Yes, sir.
Yes.
I think we have a very vague idea about the instrumentation required for isotope hydrology. An idea about what instrumentation is required would be really helpful.
Yeah. Well, the good news is that in the last decade or so, there's been a real transformation in the instrumentation necessary to make these measurements of stable isotopes of oxygen and hydrogen from water samples. And this is a technology called laser spectrometers. And what it's done is it's put these measurements in the hands of mere mortals like me, and you don't need a PhD in geochemistry to use them. They cost about $60,000 or $70,000 US, but for many countries, the IAEA is actually purchasing them and distributing them through labs in countries around the world. And I would encourage you to talk to IAEA about opportunities for that in India. But now, even if you don't have your own device, you can send samples away, and they're about $15, $20 per sample to have analyzed. And you can then think about how many samples you have and whether it makes sense to buy your own machine. The really exciting thing is that there have been some papers recently taking these machines into the field. You need electricity, and this is maybe where the comment about working in urban systems can be have added appeal. But boy, field-based deployment of these things really opens up new understanding, because now you can sample in very high frequency that you couldn't just by taking water samples directly from the stream.
Professor Datta, can I have a question? Lakshman here.
Yeah, I have a question.
Yeah. Professor Jeff, again, thank you for another exciting presentation. Thank you very much.
Thank you. Thank you.
I just had one small query for you. With the kind of measurements that you have on the xylem and for the sap, could you estimate the residence times within the trees, large trees? Do we have any idea?
Yeah, that's a great question. We've done that recently for some trees in China growing on the Lus Plateau. We used a different isotope, tritium, a radioactive isotope, to do that. On the Lus Plateau, there are very, very deep soil sequences, as you might know, maybe 100 meters of this wind-blown silty material. And there's been a very large afforestation effort, of course, on the Lus Plateau trying to combat erosion. And in this very deep Lus soil is a beautiful expression of the tritium signal in the atmosphere that has existed over the last 75 years. And as you may know, with tritium, it peaked in 1963. We then had the Comprehensive Test Ban Treaty, because these are a byproduct of nuclear explosions, and then it's declined ever since. And in that deep soil, it's a beautiful preservation of that signal. Anyway, to make a long story longer, many of the trees they're growing put roots down through that beautiful tritium distribution. We can characterize it in the soil water. We can sample the xylem water, and we can actually age date the tree xylem water that way. And shockingly, the xylem water, actually these were apple trees, so more precisely we age dated the apple water. It was 30 years old.
30 years?
30, which is, we would have expected more like months, or maybe, I don't know, weeks, months. This is a really extreme example because it's an arid zone, and the trees are kind of growing in an area where maybe they wouldn't naturally grow. But it's just illustrated how isotopes can really reveal some striking things that in hindsight seem obvious, but you wouldn't have imagined that without some of that evidence. The tough thing, though, in terms of age dating the xylem water is that you often need a more artificial signal to apply and look at. So we've been doing work in some lysimeters that have trees growing in them, and we can get at your answer there, but it's still a field challenge to do this in natural systems. But as I think you're getting at, man, if we knew that, that would really be a game changer for hydrologic models that are making such strong engineering assumptions about really a biological process.
Yes.
Yeah.
So would you tend to believe that the plant itself is exercising some kind of biological control in conserving the water?
Oh, for sure. I mean, through stomatal openings on the leaves or needles. So plants are, down regulating their water behavior based on vapor pressure gradients, based on soil potential. I think just like we have Darcy's law for water, Ohm's law really is the one to describe the plant behavior in terms of the differences in potential through the plant water system. But the isotopes can be very helpful because they're tracking the water molecule, and we're able to query things going on in plants from a hydrological perspective for the first time using these kinds of tracing techniques. Yeah.
Thank you very much. Thank you.
Yes, there are the questions, Professor McDonnell. There are the questions from the participants. One of the questions is quite interesting questions is that that's from Aniruddha from MIT Mysore. Will the field hydrological research bear fruit without substituting the modeling? Basically, he's asking it that if you don't do the modeling, our field research doesn't make any publication. I think maybe that's what our very interesting finding.
Yeah,
what is your view?
Yeah, I'm not sure I fully understand the question, but I think that maybe the point is that there's a lot of opportunity to combine field work and modeling. And I think we can learn about field processes through modeling, because if we run a hill slope model, we can then go into the field to see if indeed those processes simulated by the model are consistent with our field measurements. So that can be helpful. And the field measurements can, of course, be used to evaluate the model and hopefully reject it, because that's the way we want to do hypothesis-driven science. The model structure is merely a hypothesis, and hopefully we reject that null hypothesis and we propose a new model structure. So the two definitely go hand in hand, and I think, you know, where it's at is this dialogue between experimentalist and modeler, and the experimentalist helping to provide information on model structure through their perceptual model, and the modeler may be guiding where the hot spots for field measurements could be based on uncertainties in the model. I think that's maybe a good way forward. And so it's not an either or. Again, it's again training, I think, our students to be adept at both of these kinds of approaches.
There is another question from Dr. Ganeshri. Does isotope hydrology based studies can provide insight on cloud bursting phenomena and the flash floods?
Did you say cloud frosting or
cloud bursting?
I don't know the second word. Cloud
bursting.
Okay.
And the flash floods.
Flash floods.
Is that, yes.
Jeff, I think what she means is cloud burst.
Oh, cloud burst. Yeah. Well, I'm not sure. I think you would need to be able to sample the cloud burst, and of course these are often very isolated convective events, and whether you're lucky enough to have a sequential rainfall sampler under a cloud burst, that could be challenging. But I mean, it would enable you to perhaps trace that water from that cloud burst in a flash flood. I might say that regional climate models, some of them are now using isotopes to evaluate their model structure for how they might estimate where cloud bursts would be. So there's a recent paper using NOAA-MP. NOAA is a regional climate model. It's used widely around the world, and they've got an isotope-enabled version of NOAA-MP. And that can be, the isotopes there are helpful to say whether the model is working for the right reasons and maybe predicting where cloud bursts might occur.
Oh, so there is a question from Mr. Kaushik. He has appreciated your work, talking about recent paper, he read it. His question is, how is it decided what isotopes to be used? Given that we don't actually know how old this water is going to be. Could like to talk on this.
Yeah. Well, we don't have a lot of options for isotopes in hydrology. It's really the isotopes of oxygen and hydrogen that we're restricted to for our kind of modern systems that we're looking at. If you're looking at much older water, you can use carbon isotopes or other types of isotopes that are used more in geochemistry or biogeochemistry. But you're right, we don't know the age of the water a priori, and there's a lot of water in our catchments that's much older than the water I was describing. So, for instance, there was a lovely paper led by Scott Giesecke. He's a professor at University of California, Santa Barbara, and he did an analysis of world groundwater wells. He had access to about 6,500 of these wells, and he age dated that water using carbon isotopes, or he he did a meta-analysis of the carbon isotope data that authors had presented. Anyway, what he found was that for groundwaters below 250 meters, 2/3 of the groundwater around the world in those wells is 10,000 years old or older. That's, for me as a hydrologist, really a sobering number. That's not that deep in the scheme of things in steep headwater basins. Think of how steep your systems are in the Western Ghats or in the Himalaya. Below 250 meters, 2/3 of the world's groundwater is fossil water older than 10,000 years. And this is, I think, one of our great challenges in catchment hydrology now, how to reconcile the very long ages of water in our storage with the much younger water we see in the stream. Another paper that Scott led, these are all published in Nature journals, this was a couple of years ago, he found that of world streams, about 1/3 of global river flow is less than 3 months old. So you've got this juxtaposition of a sizable fraction of really, really young water in stream and a sizable fraction of very, very, very old water in storage. And how these two kind of come together in our larger watersheds is still something we don't really understand fully. I showed you a very small window into hill slopes and headwater catchments today, but I think this question's maybe getting at some of those extreme challenges, and we're just limited by the technology, by the tracers that we have, which is so unfortunate, and I think why we need to work with modelers, because we need models to help us maybe pose hypotheses and checks that we can then do in the field.
We have a lot of questions, but I think I have to wind up these things. So there is a questions from Vaibhasa Baduri from IIC Bangalore. Okay. He is a big fan of your work. Okay, that's a good thing. His question is for imperial streams. To what extent do you believe that the irregular measurement affect the determinations of correct transit times of conservative tracers?
Did you say imperial streams? I missed that.
Yes, yes.
What does that mean, imperial stream? Or ephemeral stream, or?
Yeah, permanent streams. Yes.
Permanent streams.
Yes.
Yeah.
No, maybe ephemeral.
Ephemeral.
Yeah.
Yeah. So the question is, for ephemeral streams, what information we have on transit time, or?
Yes.
Yeah.
The irregular measurements affect the determinations of correct transit times of conservative tracer.
Yeah. Yeah. Yeah, and that's another issue. So the sample frequency has a big bearing on your estimates. And again, there's a lot of research going on in that regard. I think this question is a good one, in that these things are highly uncertain, and that uncertainty increases with decreases in measurement frequency. And I think that this is where the hope of, in the future years, being able to take laser specs into the field and get high frequency measurements, that will really open up better understanding of these transit time distributions. One thing that we've learned that I've not talked about today is that rather than one kind of master transit time distribution for a catchment, that distribution's changing through the year. In the wet season, it might be one way, in say a winter, another way, in other transition times, depending on the climate, it could look differently. So it's a very time varying transit time distribution. And I think maybe that's what this question's alluding to. If we don't sample frequently enough, we don't see those time varying changes in the transit time distribution, and we introduce a lot of uncertainty into our estimates. So yeah, right now I think we're still in a very kind of brute force mode, and yeah, we're looking forward to new graduate students to push this forward.
Why not the changes day to day? Why don't you expect the changes to be day to day, hour to hour? Transit times may change day to day.
They can, and there's some new work showing not day to day necessarily, but flow condition to flow condition. We have a site in Oregon where in the summertime when the flow is so low and only a few groundwater seeps are keeping the stream going, the age of that water goes to like 50, 60 years. That's how old the water is, because it's just those little groundwater seepage areas, a very old groundwater that's sustaining the flow. Then when the rain turns on and it gets very wet, that fades into the background. It's only a very small amount of the total flow, and the age of the water is reduced to maybe 1 year. So yeah, I think it's very flow dependent, and this can help us diagnose our systems and how sensitive they might be to climate and land use changes.
We can have the last questions, which is quite general questions. Mr. Pandu Sethi, can you expect satellite measuring the stream flow for us in near future? Yeah, I mean, there's a lot of work going on with, I think it's SWAT, the SWAT mission, not the SWAT model that we talked about on Monday, but SWT missions.
Yeah,
that's the SWT.
Yeah,
yes.
I have no experience with that, but I have colleagues, a friend of mine who runs the Water Survey of Canada, Al Pietranero, he's involved with that with colleagues at NASA and the UCLA. But yeah, it seems quite hopeful, but maybe for larger rivers, not small headwater streams, and that's the challenge. If you look at the percent of first order streams, they control the distribution of water courses in India or North America, and there's millions and millions of them, but they're very small. So measurement from even using SWAT is a challenge, and that's where most of the water comes from. So it is still a measurement challenge, and it's quite remarkable that we're still having this kind of challenge. One thing that's been transformational, and you probably have people in the audience that use this, is GRACE, the gravity satellite. We have Jay Famiglietti here as the director of our institute, and he's used GRACE to show, again, at larger scales now, changes in groundwater storage and changes in water cycling. And I guess it's that combination between maybe remotely sensed stream flow, remotely sensed storage change, where maybe we'll start to understand these things in a more global or regional way.
Well, so this is okay. This is, I'll put it the last questions. Is already we have. This is questions from Dr. Sushma Sudhistri, Indian Agriculture Research Institute, New Delhi. Her question is that using the tracer methods, it's very good methods. What may be the reason not used in India? What's the reasons for it's not used in India?
Yeah, I mean, I don't know. There's always lags from the latest papers and techniques used. I think it goes back to education and training. These techniques are often not taught in even graduate courses in hydrology. I think, many of us come from engineering traditions, whether it's civil or agricultural engineering, and we think of our systems in less biological terms and maybe more physics terms. So I think the reason why we don't see immediate adoption of these techniques is that there are lags in the system that you were talking about in the panel discussion earlier. And I think it does go back to training. It does go back to dissemination of information. And it is a slow process, and it's not just a slow process in India, it's a slow process in terms of adoption around the world. I think we want to be hopeful and positive, and the kind of things that you are talking about in terms of community building within India, coming up with standardized training or teaching, thinking about graduate curriculum that could then start to influence how students perceive this information, that'll be very helpful. So, yeah, I think that the reasons are natural, and it's not unique to your region. It's implementation is slow.
That's true. That's true.
Yeah.
So I think with this, I think just Professor Poti can give thank you to Professor McDonnell. I think the questions and answer side is over. I just hand over to Professor Poti to give some remarks.
Okay.
Professor Poti.
Poti, you have to unmute. You have to unmute.
Sir, your audio.
Professor Jeffrey, it has been a tremendous 5 days for us. I have few words to describe about your lectures and the proceedings for the 5 days. So let me just thank you and all the presenters, all the resource persons that have been useful to us, that have helped us. I have nothing more to say. Well, during the conclusion, I have a few sentences to tell, not at this juncture. Thank you again, that's all.
Thank you.
So now we can go for, I think, thank you, Professor McDonnell. Really, we really, I agree with Professor Portis. We are enjoy the sessions, and
thank you.
Definitely, you encourage our undergraduate and graduate students who are been in a YouTube live, and this documents will be there. All your YouTube lives, and your presence, these 2 lectures. Really stimulate to us to think beyond what we have been as engineering, looking only Hutterian equations. I think that's what today you have changed it. We have to looking things that. Thank you, sir.
Right.
Thank you, sir.
Thank you very much. Pleasure. Bye.
Sir, we will start validatory things or what? Professor Poti?
Professor Datta, it is better we go towards concluding the event, concluding the workshop itself.
Yes, that's a bit already 7. It's quite interesting. Yeah.
And you will first on behalf of the IIT, you will do the vote of thanks, and then I will just speak a couple of words. Okay, that's all.
Yes,
we shall conclude the session. Conclude the
okay. So, good evening to all of you who have been still in with this online webinars. Really, we enjoyed last for 5 days, and that is what is happened because of contributions of not from only from IIT Guwahati or NI Mysore, but because of you, your presence and your attending these lectures through YouTube Live, as well as you really encourage us, like what I'm to highlight it. The first lecture itself having more than 700 hits. Okay, that's what is showing it. And all of others lectures, second day and third days is more than for 300s. So that's what is quite encouraging for us. And that's what, even if these 5 days really encourage, really tiresome, but it's really enjoyable to learn many things. The last lecture presented by Professor McDonnell is really beyond a point. So let me, I'm very short to thank all of you, all first the participants, then I'm coming back to this to thank Professor Jeffery McDonnell, as you have really waking up in early mornings, delivering the lectures. If you look at that's the morning of 6 a.m. So if you look at that and how much energy he spent it to deliver the lectures, that's what could be the lesson learned from many of us to can deliver this level of lectures at the early morning at 6 a.m. But that's the reason a heartfelt thank from whole organizing team. Also, I on behalf of those participants also, we want to thank him for this these 2 lectures and the supports what he provided for these webinars. After that, I just want to thank the speakers or the panel members who joined, like Professor Mudhu Sekars, ISC Bangalore, Dr. Laurent Reeds, INRE France, Dr. Silas, NCSS, Professor Lakman Mani, Nandagiri, NIT Suratkal, Karnataka, Dr. Manish Kumar Nima from NIH Roorkee, Dr. B. Venkatesas from NIH Belugura. So those lectures really made us very interesting things and update the things like what the instruments are happening at the critical zone observatories. That's really grateful for all of the speakers to brought it and complete all these webinar programs with the time frames. That's then I would to just have a Dr. J.S. Pariyars and Professor A.K. Sharma who nicely conducted these sessions, as well as I want to thank the Professor T.G. Sitaram, Honorable Director IIT Guwahati, and Professor Rohini Nagapadma, Principal NI Mysore, for really encouraging for us to do these activities as well as I want to thank the Professor K.C. Manjunath, Head of the Department of NI Mysore, Department of Civil Engineering. That's really it's a encouraging part to do these 5 days work. And with this note, I just want to conclude my thankful note here. Professor Poti, just to conclude, just keep conclude address.
Thank you, Datta, for handing over me the mic to conclude the whole event. I will be a little emotional, I believe. In India, we say, Karmanya Vadikaraste na phaleshu kadachana. It means you have rights over your actions, never over the fruits. This is a very famous piece of advice given by Krishna, the Lord, to Arjuna, his disciple, who was waging a tough battle against his cousins. In simple words, this advice means do your best and let things shape their own way. This is exactly we the organizers have done with regard to organizing this workshop. It all started when I first wrote to Professor Datta and spoke to Professor Shekhar the same day about 7 weeks back. Both of them instantaneously agreed to the idea of working together. Not having known me, Professor Jeffrey took about a week's time to respond to my call. Once he accepted to associate with us, it was a near cakewalk and everything went on smoothly. All of us wanted to bring out more than a simple webinar for getting a score. We wanted something new and much more creative than the common webinars. We then worked as a family. The team at NIE took to planning and furnishing the material. The team at IIT shouldered the responsibility of conducting the show. They connected to resource persons from various quarters, planned on real-time need, and very effectively carried out the job of broadcasting almost immaculately. Professor Shekhar reached out to his co-workers and planned the presentations on CZWs to suit our tunes. Professor Jeffrey, the center of attraction, enjoyingly joined us, true to his known affection for field hydrology. All the speakers took special interest in contributing their mite to this workshop. The participants, on their part, came forward enthusiastically with questions and made the proceedings rememberable. To summarize, the 5-day event has turned out to be a great success, as we, the promoters, believe. Participants are always welcome to put forth their suggestions to improve our performance. Javed is telling something.
Yes, I think Dr. Kuti, if you have concluded, I would like to thank Professor Datta and Dr. Kuti for their
It's a great pleasure. Okay, we should not take it.
You will come.
We are now one family now. Last 5 days we have bonded ourselves virtually. It's a family. We are now
a family. Should not go on thanking each other. That's my intention.
There's one more group to be thanked, and that is the group from IIT Guwahati, and Dr. Suresh and Dr. Ashish, and I'm sorry, I'm not able to recall all the names, but then personally I would like to thank the efforts that your group has put in, and Microsoft Live was something new and they did a very excellent job. I would like to thank on behalf of this workshop your team, sir. Thank you very much.
Thanks. It's a pleasure. It's a pleasure, slot.
It's a pleasure. But I have another line to add here. The participants always have their freedom to put forth their suggestions to improve our performance. If we venture into a new experiment, in fact, we have men and material sufficient to bring forth one more workshop, but we fear the new venture would not turn out to be as remarkable as the one we are now concluding. So let me conclude with the Indian phrase, Sarve Janaha Sukhino Bhavantu. Let all live in peace. Thank you all.
Thank you, sir. Thank you. Thank you. You can have a watch.
Thank you. Yes.
Thank you.
Must yes.
Thank you.
See you. Shall we depart?
Yes, sir. We will conclude now. Bye.
Fine, Javed. Thank you all.